welcome back. In this review lecture, we will be covering energy conservation, particularly the first law of thermodynamics. So, let us simply take a case, an example, a very primitive example. So, this is basically a room well sealed and well insulated, having a refrigerator with an open door. So, what do you expect? Do you expect the room to get cooled, or you expect the room to get warmed up? So, intuitively you may think that because of the purpose of the refrigerator, you may assume that the room will get much more colder, but in practice what is happening, because this is a well sealed and insulated, the electrical energy is being used in order to run the refrigerator now, which is now open. So, thus your thermal energy of the room gets increased. So, this is a one form of conversion of electrical energy into different form of energy. So, temperature should rise in such case. Now, there are many examples, but when we talk about thermodynamics, we often deal with energy and its transformation. Okay. So, let me just first talk about the different forms of energy. Okay. So, these are thermal, mechanical, kinetics, potential, electrical, magnetic, chemical and nuclear. Now, the total energy of the system consists of all forms of energy provided to the system. So, there are two parts of the energy. One is a macroscopic energy, which is kinetic and potential energy. Another one is which is related to the molecular motions or related to the molecular structure are called macroscopic one, okay, which is independent of outside reference. Whereas, of course, macroscopic does depend on the outside reference. Now, sum of all this macroscopic form of energy is called internal energy, which we often use U to represent. Okay. So, let me just describe quickly what a macroscopic form of energy. Okay. Now, these are related to the motion, influence of external fields such as gravity, magnetic field, electricity, surface tension. Kinetic energy is part of the macroscopic form of energy, kinetic energy and potential energy. Kinetic energy, as we know, is simply this. Okay, the kinetic energy system associated with its relative motion with reference frame. Potential energy is due to the elevation in a gravitational field given usually by mgh. In the absence of magnetic, electrical and surface tension terms or effects, the total energy consists of internal energy plus the macroscopic energies, kinetic energy and potential energy. Okay. And so, this is the total energy of the system in absence of magnetic, electrical and surface tension term. Now, if you consider a system such as this particular closed system, now since it is a closed system, mass does not get exchanged with the surrounding, but you can exchange heat and work or exchange energy with the surrounding, which can be in the form of heat or work. So, let me just focus first on the work. So, work is basically energy transfer associated with the force acting through a distance. So, a rising piston, a rotating shaft and an electrical wire crossing the system boundaries are all work interaction with the surrounding. Okay, one can prove that also. Typically, what we refer work or the symbol which we refer from state 1 to state 2 is given by W12 or simply we use W. Okay. Sometimes we often use small w to represent work done per unit mass. Work done per unit time is of course power. Okay. So, formally there are many sign conventions, it primarily depends on the textbook which we follow, but it is just to make our life little easier. So, we will be using one of the sign convention, but one of the way to do that is we consider heat transfer to a system positive and the work done on a system negative. Okay. Or if you know the exact interaction with the surrounding, you may not use the sign the way we have stated here. We can simply write it based on the actual sign. Now, usually the signs are used when we do not or we are not aware of the effective interaction with the surrounding, and thus this assumption helps us in solving the problem. So, both heat and work are recognized at the boundary of a system as they cross the boundary. That means they are boundary phenomena, Remember that the system possesses energy but not heat or work. They get realized only at the boundary. Okay, both are associated with a process, not a state. Unlike property, heat or work has no meaning at a state, and both are path function. So, this is the reason that the change, we do not consider the change in the work or change in the heat. Okay. So, both heat and work are path function, and their magnitude depend on the path followed during a process as well as at the end set. So, so let us consider a process diagram here, this P and V, okay, and this is process 1 and 2. So, in this case the change in the volume is 3 meter cube, and the change in the volume for the process B is also 3 meter cube, because volume is a property of the system, and hence the final and initial state, even though it has the two processes are following a different path, the change in the volume are going to be same, but the work associated with this, which actually depend on the area under this curve, will be different. Okay. And this is the reason that we actually write the work usually in differential form delta W and absolute form W, okay, and never we write W when you integrate. Okay. Now, what are the mechanical form of a work, because their work can be mechanical and non-mechanical form. So, what are the typical definition of the mechanical form is simply the force into distance. You need a force in order to move the boundary. Okay. You can move the object here. So, force and distance is nothing but work. Examples are shaft work, spring work, surface tension work, and in addition to the mechanical work, we have electrical work, magnetic work, electrical polarizable work, and so forth. Okay. So, let me just come to the formal definition of the first law of thermodynamics. So, first law of thermodynamics states that energy can be neither created nor destroyed during a process. It can change only its form. Okay. So, in other words, a first law says that the change in the total energy during an adiabatic process must be equal to the net work done, because adiabatic means there is no heat supplied to it. So, if there is a change in the system and there is no heat supplied to it, so it will be associated with the work. Okay. So, this is an example of the first law representation. So, for example, if you have a mass falling from a cliff having a potential energy is 10 kilojoules with no velocity or kinetic energy, after reaching a certain distance it will, assuming there is no friction loss and so forth, it will some of the potential energy will get converted into kinetic energy. This is a classical example, textbook examples of that. Or you take an example of the heat supplied to the potato, any change in the energy of the potato will be due to the heat, and if there is no losses it will be exactly the same. Now, take an example of let us say container or the boiler supplied here. So, in this case if there is no work interaction with the surrounding, that means no work supplied or provided to it done by the system, then the change and the energy change of the system is equal to net heat transfer. So, that is a statement directly from the first law. Okay. Similarly, if you consider an adiabatic system where the electrical work is done on this adiabatic system, so whatever the work is being done will get affected by the change in energy by the same amount. Okay. And that is the same thing as far as the work, shaft work is concerned. Shaft work in supplied to the system, the amount here will be same as the change in energy of the system. Okay. So, that means we can formally write that total energy entering the system minus total energy leaving the system should be equal to change in the total energy of the system. So, in other words, E in minus E out is delta E system. So, and E is complete, E is basically the internal energy, the potential energy and the kinetic energy. Okay. So, let us take an example of this cylinder piston where the boundary work here, okay, which basically is the energy, the work supplied to this piston is 10 kilojoules, and if it is adiabatic, that means the change in energy of the system will be same as this. There is no heat interactions here. In this case, you have a system where the shaft work is supplied, but there is a heat interaction. Certain heat is being supplied here and certain heat is lost to the surrounding. So, considering this basic definition, the E in minus E out is equal to E system. So, what is delta E system? Okay, this will be 15 minus 3 plus 6, okay, is equal to 18 kilojoules. Now, this is where one has to little bit consider whether one has to directly take use of a standard sign convention or simply the sign of this. So, for the simple sign, of course, we know that Q in is 15, okay, plus 6 minus 3, that means the quick heat in, work in minus work heat out, that will be equal to the change. That is one way of looking into it. So, this is total energy supplied, total energy entering, okay, and this is your total energy leaving the system, that is based on that. But if you consider the sign convention, then sign convention says that, well, heat supplied is positive and work done by the system is negative. So, in other words, delta E is Q net in minus W net out. Okay. So, what is the Q net in? Is nothing but 15 minus 3. Okay. What is the W net out? Is minus 6, and the minus of minus 6 is nothing but plus 6, and thus you can use this sign convention as well as the basic definition without considering the sign, just looking at the known interaction directions. So, let me just further continue. Here the energy change is nothing but E final minus E initial of the system, okay, and delta E is nothing but delta U plus delta KE plus delta PE. Of course, delta kinetic energy is related to this. If there is a change in the velocity of the system, then of course you are going to consider that. If there is a change in the elevation of the system, you will be considering the delta P. But most of the time we ignore that. Okay. For the stationary system, so there is no change in the elevation. So, delta P is going to be 0, delta V is going to be 0, and hence delta E is nothing but the change in the internal energy. Okay. So, but that was the what we considered earlier was basically for the closed system, where the mass interaction was not there. But in generally there could be mass interaction. So, we will consider the control volume for the flow system. So, we have mass interaction, that means masses can come in and out and work, and as well as heat interaction. So, energy can be transferred to or from a system in the form of heat transfer, work transfer, and mass flow. Okay. Whereas for the closed mass or closed system, which involves only heat transfer and work. Okay. So, a general definition in that case would be E in minus E out is equal to E delta E system. Okay. So, E in minus E out is delta E system, and what is E in here? E in is equal to is nothing but Q in plus W in plus E mass in minus Q out plus W out and plus E of mass out. Okay. And so, you can rearrange this in this form: Q in minus Q out plus W in minus W out plus E mass in minus E mass out. Okay. So, this would be useful if you are aware of already the interaction directions, the way it is happening. Okay. Otherwise, you can always use net effect, net transfer. So, this would be also like net in, net this will be net in, net work in, net mass in is equal to E system, delta E system, and that is the reason that you can write in a compact expression as net energy transfer by work and mass is equal to change in the internal energy, kinetic energy, potential energy of the system. Okay. One can write in a rate form in this. Okay. So, this is a rate form expression, we put it here dot, which essentially means for a constant rate, that means delta E system, this will be the case. You can find a delta E by considering delta T, multiplying this expression by delta T. Okay. For a closed system undergoing a cycle, of course, delta E is equal to 0, and in that case the heat the net heat supplied is equal to net work out. Okay, that means Q is equal to W. That is what it is written, net Q net is equal to W net. Okay. Remember, this is nothing but this in and this is going to be out, okay, for a cycle. That means net heat supplied is equal to net work out done by the system. Okay, so with this basic definitions and review of the first law, we are going to just end this lecture with a simple example. So, this is an example of a fluid within this rigid tank is cooled while being stirred by a paddle wheel, okay, which supplies work of 100 kilojoules, and during the cooling process the fluid loses 500 kilojoules of heat and the paddle wheel, as I said, does 100 kilojoules of work. So, find U2. Initial internal energy is given to us. So, of course, the system is stationary, it is not moving, and considering that, we will be considering, of course, the changes in the potential energy, changes in the kinetic energy is going to be 0. Okay. So, that means delta E is nothing but delta U. So, with this we can use two ways to solve this problem. One, considering again sign convention, which says that delta U is nothing but Q net in minus W net out. Delta U is nothing but U2 minus U1 and Q net in is minus 500 and W net out is minus 100. Okay. So, which means this is minus 400 kilojoules, and thus your U2 is 800 minus 400, this is 400 kilojoules. So, this is one way of solving. So, we also said in other expression that we can write E in minus E out is delta E system. Okay. So, this is a net energy, net heat in, net heat out, net mass in, that will be delta E system. So, delta E system is of course U2 minus U1 and net heat in is, so this is a compact form. So, net heat in is again minus 500, net work in is 100. So, in other words, this is minus 400 kilojoules is U2 minus U1, okay, and this is same as this. So, this also gives us 400 kilojoules. Okay, so that is the end of this particular lecture. So, we will continue this fundamental understanding in initial few lectures and I will see you next time.